Hello, here's some more practice on simple harmonic motion. Starting off, they're giving us a little tick box exercise to do here. We've got an object oscillating with simple harmonic motion. Place a tick in the box for each true statement. Right, the acceleration, is it in the opposite direction to the displacement? Yes, it is. We know for SHM that, that is one of our key things, isn't it? So the acceleration is equal to minus omega squared s. So we're getting this opposite direction, this minus sign, because we've got a vector here and a vector here. So that's definitely true. Is it directly proportional to the amplitude squared, the acceleration? No, it isn't, because the acceleration is minus a omega squared, say sine whatever function we've got of the phase. So no, it's just proportional to the amplitude. It's not proportional to the amplitude squared. So we've got no tick there. Does the acceleration increase as the displacement decreases? No, it doesn't, because, well, displacement is a vector, so it depends which way we're going, in which direction. So it needs to be symmetrical. And if we've got a vector, then we need the same thing to happen in both directions for positive and negative displacement. So that can't be the case. And does the acceleration increase as the speed of the object decreases? Yes, it does, because we're getting maximum acceleration at the amplitudes and we're getting maximum velocity at the equilibrium point. So we've got this this interrelation here, which you see from the when you're differentiating things, when you're going to sine to cosine, or cosine to sine, whichever way around you happen to be doing it, from velocity to acceleration, you're getting that the gradient of the velocity is the acceleration. That's what we expect anyway from all motion. That's what we're doing when we're differentiating to move down this sort of hierarchy of descriptive terms. So yes, the acceleration does increase as the speed of the object decreases. So we've got two ticks, top and bottom, and then not in the middle. Right, so now we've got a graph showing, it's velocity again. They like doing this just to make things a little bit more difficult. Let's see what we're going to get off of this graph without even looking at what the question is. We got a V max here, which looks as though it's going to be about 0.08, say, so 0.08 meters per second. That's our V max. We've got it's a nightmare trying to read the period off of this. It looks as though it's not actually starting at 0, but going from there up to here, we're a little bit, well, it's hard to tell. I'm going to go for 1.2 because I can't tell exactly where all these things are crossing the lines on here. But I'm going to say that t is equal to 1.2 seconds. That's completing one cycle. So we've already got that there, which means we know that the frequency is, if the period is 6/5, the frequency is going to be 5/6 hertz. We know that omega is 2 pi f, so omega is going to be 10 pi over 6, so 5 pi over 3 radians per second. So that's our omega. We know that V max is omega A. V max equals omega A. So 0.08 divided by this omega. So we're going to have amplitude is going to be equal to 0.24 divided by 5 pi. So I'm going to tap that into the calculator now. What is that giving us? 0.015 meters. So we've got all of that out of it. What else could we have? We could have the A max, seeing as we've got V max and S max, because amplitude is S max. So A max is A omega squared. So A omega squared is going to be, well, let's cancel one of the omegas. So we'd have 0.08 left, and then we're going to have to multiply by the other one of the omegas. So 0.08 times 5 pi over 3 is giving us 0.42. meters per second squared. So we've worked out a lot. I think that's going to be pretty much everything that we've got in SHM. So what have they asked us in the question? Frequency, yeah, we got that here. Amplitude, yeah, we got that there. And maximum acceleration, yeah, we got that there. So, I mean, you know, what else are they going to ask on these sort of things? So that was all pretty good. Part C, with the help of a suitably labelled graph, explain what is meant by resonance of a mechanical system. Okay, it does certainly makes it easier drawing the graph. So let's draw in, we know we're going to have some kind of peak amplitude going on here. We've got on the x-axis, this is driving frequency. So let's label that on, and that's going to be in hertz. You might as well put the units. This is going to be amplitude in meters or centimeters or whatever, anything that's got some kind of length on it. We're going to need to mark where the peak is, and we need to say that this is, I don't have enough space at the moment here, the natural frequency. Let's call that F0. So yeah, you can then say something along the lines, remember we've got to come back to this part of the question, but for this one you'll want to say, well, you just want to describe this really and say when driving frequency equals natural frequency, there is maximum amplitude of oscillations. But you know, write it in more of a sentence rather than note form. Right, so the second part, state and explain an everyday example of resonance. So let's go for, I always go for the child on a swing. Child on a swing. So the swing has begins with, I'll come back to what I've said, begins with natural frequency equal to 2 pi root L over G. That's a pendulum just oscillating. So if the driving frequency, i.e. pushing the child, so something a bit more than just saying push, if the driving frequency equals the natural frequency, then amplitude increases. I mean, the reason I put begins here, you wouldn't have to explain it in this answer because they only give you a couple of marks normally for these sort of things, one for the example and one for the explanation. So I put begins because, of course, as soon as you start getting away from small angle, this natural frequency would change. But of course, when you're pushing someone on a swing, you change your driving frequency to match the natural frequency. I mean, you can see the natural frequency happening if you just keep on pushing at the same point. But the length of time between your pushes will change as the angle increases because we've no longer got a simple pendulum. So yeah, I mean, when you're giving this description, what they're really wanting you to say is what is the thing being driven, i.e. the swing, and what is the thing doing the driving, pushing the child on the swing. So if you've got those two things in and you're showing the difference between those two, then you'll be fine along with the example, and dropping in as usual bits of key terminology. You know, keep mentioning natural frequency, driving frequency, amplitude, things like that. So yeah, not a fairly straightforward question, this one. Quite a nice one, covers a lot of bases.